We're going to hear from Deborah Persaud, the physician at Johns Hopkins Children's Center. We'll talk about the HIV/AIDS epidemic and the focus on children that has changed the whole attitude towards AIDS. She worked as part of a team that showed a baby had been cured of HIV virus by giving it anti-HIV drugs, and won the Elizabeth Glaser Scientist Award, was featured in Time Magazine's Top 100 Most Influential People in 2013. And this year, she's contributed toward a second baby being cured of AIDS. So let's hear from Deborah Persaud.
Good morning. It's a great honor to be here and really a fantastic experience yesterday hearing from everyone. I will say that we haven't cured babies of HIV. The case of the Mississippi child has rebounded, and I'll provide the insights we've gained from that case. And the second case has not been cured, has been treated very early, and has no detectable virus on antiretroviral treatment. But these cases continue to inform the field. So my basic topic and focus here is to try to take you through a journey and my journey in the field of pediatric HIV/AIDS infection, and really highlight how studies in children have continued to inform the field with respect to HIV pathogenesis. So this was, my journey started in this field in 1981 when I was a medical student in New York City at Bellevue Hospital. So I entered in 1981, and this was when the HIV/AIDS epidemic emerged, and this was really the face of our wards at Bellevue Hospital. It was filled with patients looking like this, and as Lori Garrett presented yesterday, and it was really a very moving part of this, is really human contact was very limited with these patients. They were actually in rooms, and we wore gowns and gloves before we entered the rooms, and particularly for children, this was a very isolating experience. And so it's really great to stand here now, 30 years later, to really be able to say that the direction we've taken to be able to begin to talk about, thinking about changing HIV to a curable disease. And so what I've highlighted here is really the timeline for this disease. And what you see is how quickly we went from an unidentified process to identifying this as an infectious disease process, leading to testing and then the beginning of antiretroviral treatment. And what you should note on this slide was really the identification of cases in women in 1982, and then quickly followed by cases in infants that highlighted or signified that we were dealing with an infectious disease agents. Prior to that, it was a disease of gay men and intravenous drug users and hemophiliac. And again, it was the first case in an infant who acquired infection through transfusion that signified that we had a tainted blood supply. So by 1987, AZT, or zidovudine, which is a nucleoside reverse transcriptase inhibitor, was licensed for treatment of HIV infection. We've now moved much further. Over 20 antiretroviral drugs are now approved for treatment, and they're combined and are highly effective in controlling HIV from replicating. And so in the early 80s, the late 80s, early 90s, in my training, when HIV-infected women presented for care, these were the numbers we gave them. You have a 25 to 40% or 1 in 3 chance of transmitting the virus to your child. We have no interventions that could prevent this transmission. And this really dismal news to infected women is what led obstetricians and pediatricians and mothers to begin this notion of thinking of using antiretroviral drugs to prevent transmission of infection. Now you have to realize this was mostly a disease of underrepresented minorities. These were young women, pregnant women with a drug with unknown teratogenic effects or effects on the fetus. So this was really high risk research with needing an ethical framework for its performance. And so while there was concerns over toxicity, really the outcome was so dismal that I think the risk was really worth it. And this is what led to the landmark study that's really changed the face of pediatric HIV/AIDS around the world. And this is the seminal study, the PACTG 076 trial, that really looked at the capacity of giving pregnant women AZT. And this study was done in the US and Europe after 14 weeks of pregnancy. women got AZT by vein or intravenous administration during the labor and delivery process, and then the infants received AZT for 6 weeks after birth. And with this study, what we found very quickly, and the study was closed prematurely based on the Data Safety Monitoring Board, where 67% reduction was seen. So what you can see in the placebo arm, the transmission rate was about 25%. With AZT, there was a reduction to 8%, so 67% reduction. And this became the mainstay of our prevention efforts and still is in the United States. And so this is during my professional development from 1981 to 1985 when I graduated from medical school. HIV/AIDS was not preventable in infants, and you could see this rise in AIDS through the 90s and then this precipitous decline following the identification that AZT alone could actually prevent mother-to-child transmission. I continued my research I pursued a residency training in pediatrics at Columbia Presbyterian Medical Center, where the HIV, and there we rotated at Harlem Hospital. So the HIV epidemic was quite rampant in that area. We saw many lives being lost. So while we could prevent, we still had a cohort of children who were infected with no antiretroviral drugs for treatment. And following my residency training, I went back to New York City to NYU Medical Center to pursue a fellowship, postdoctoral fellowship in studying the pathogenesis of mother-to-child transmission of HIV transmission in infants. And so here we are today. This is really what we can, if women receive antiretroviral drugs during pregnancy and infants receive prophylaxis postnatally, the overall risk of transmission actually is less than 1%. And these numbers have been replicated in resource-constrained settings such as Botswana. Again, but you need to have access to antiretroviral drugs for prevention. And so what we've learned from these studies in women and infants, and this is a pediatrician's perspective, is really, these were really the first studies to show that antiretroviral drugs are effective in preventing HIV transmission, including through breast milk. So there have been multiple studies done showing that extended prophylaxis of the infants provide protection against transmission of HIV. So some infants receive antiretroviral drugs throughout the breastfeeding period, which could be up to a year of breastfeeding. And so these studies really provided the framework for what's being done now in adults to use antiretroviral drugs to prevent transmission from high-risk exposure and then post-high-risk exposure. So we believe the mother-to-child transmission setting has really provided the framework for use of antiretroviral drugs for prevention. So I'm going to switch now. Really the path that I've taken is that following my training and fellowship, where I studied really developing in vitro systems to study transmission of HIV infection from mother to child. I had my first child at the end of my fellowship, and then I moved to Kenya for 2 years, where I largely stayed at home and worked at a local district hospital, and I really moved because of my husband's career path. And I spent 2 years in Kenya, and this really gave me a flavor as to what living in resource-constrained settings and delivery of medical healthcare systems, the obstacles to delivery of healthcare systems. But in 1997, I returned to the United States, to Johns Hopkins University, and had the unique opportunity of joining the laboratory of Robert Silcano. Dr. Silcano is is funded by the Howard Hughes Medical Institute, and his lab identified that there were reservoirs for HIV that will serve for obstacles for cure in HIV-infected adults. And so it was in 1997 that I began on this journey on trying to identify obstacles to curing HIV infection in children, and I'll walk you through that story right now. And so the focus of my research has really been on the concept that if we can treat children early enough, or very early, as in the case of the Mississippi child, which would be in the first 2 days of life. Early therapy would be considered around 2 to 3 months of age. That if we could treat children very early, perhaps we can attenuate these reservoirs from forming and achieve virologic remission or cure. And so what's unique about pediatric HIV infection and why early therapy and very early therapy is feasible is that we know when kids are exposed to HIV, we have algorithms of testing, nucleic acid testing, that allows us to identify HIV-infected infants very early. And so by knowing timing of exposure and having these systems in place for testing, we can actually identify infected children as early as within a few days of life if they're infected in utero, or at least by 2 weeks of age if they're affected intrapartum or by early breastfeeding. And so in 1997, when I returned from Kenya, the field of HIV therapeutics had really been revolutionized, because these were seminal studies by David Ho, George Pearson, and Alan Pearson and George Shaw, showing that when patients are placed on combination antiretroviral drugs, so 3 or more drugs, what you see is really this precipitous decline in plasma viral load. So we now had ways to really considerably drop plasma viremia in HIV-infected patients. And the study that really is shown on the bottom of this slide that really raised the notion that perhaps by giving patients combination antiretroviral treatment, you could actually clear all of the HIV-infected cells from an individual and therefore lead to cure, was really this seminal study by Alan Pearson and David Ho, showing this two-phase decay in plasma viremia when you put patients on antiretroviral treatment. We see this same two-phase decay pattern in HIV-infected children also. Now what this tells us, this rapid decay followed by slow phase decay, is that HIV-infected cells turn over at different rates. And what they can do is actually estimate the turnover of infected cells. So the first phase decay is attributed to turnover of activated CD4 T cells, which turns over at about a day. And then the second phase of decay by slowly turn over, populations of cells. Yeah, that's better. And so this pattern of decay of HIV is what led to the speculation that perhaps if you treat an individual for 2 to 3 years continuously, eventually these cells would be cleared from the infected host, allowing you to stop antiretroviral treatment and prevent rebound of virus. But shortly after that, and what the combination antiretroviral drugs do is they act at multiple steps in the virus life cycle. So in the absence of antiretroviral treatment, this is a very dynamic process whereby there's ongoing cycles of virus replication, virus entry, reverse transcription, integration, full virus particle production with continuous infections in susceptible target cells. But with treatment, you can actually block this process sufficiently, greater than 99%, leading to the sustained suppression in virus replication that we see. And this is just an example of what a typical plasma viral load plot would look like. And I want you to keep this in mind when we talk about the Mississippi child and how distinct that case was from the standard treatment responses we were seeing in children treated around 2 to 3 months of age. And what you see here is you see the typical biphasic decline as I showed you, and then the open symbols represent that every time you test this child, there's no detectable plasma virus in the circulating blood using standard clinical assays. Now, occasionally what you would see on routine follow-up is what's considered a blip in plasma viremia, and what this tells you is that despite this persistent undetectable plasma viral loads, there's still persistence of cells that are capable of producing virus stochastically in these children. Now we know we've developed very sensitive assays to quantify the amount of infectious virus that persists in patients with these undetectable viral loads, and ultrasensitive assays to measure free virus below 50 copies per ml that form the framework for our studies of HIV remission and cure in infected individuals. And so, as I said earlier, there was initial optimism for HIV cure. So this idea of curing HIV is not new. It's just that we knew that it's not in 1997 based on these decay curves when Botzel Khanna's lab showed that even in patients who show that persistent undetectable viral load, if you use very sensitive culture assays, you can actually purify resting memory CD4 positive T cells, which is he identified as a reservoir for HIV in these patients. You can actually recover virus from almost all infected individuals despite the sustained suppression of virus replication. And it was this finding of persistence of HIV in resting memory CD4 T cells that really dampened the optimism towards curing HIV. So here's the model, and the model we've been working on for pediatric HIV infection. So I joined Bob's lab in 1997, which is when these reports first came out. And the model here that he derived in 1997, which I think is what the Mississippi baby highlighted with the rebound, is that it completely fits with this model now in 2014. And so what the model is that when these cells are generated in the context of formation of routine immunologic memory. So in other words, when a naive cell encounters its cognate antigen, becomes activated, these are the cells that HIV preferentially replicates and quite efficiently. During the process of immune encountering of antigen and generation of immunologic memory, a proportion of these cells on transitioning to this memory state carry the HIV genome integrated into the host chromosome. Because these cells are resting, the virus does not express itself. By not expressing viral RNA or proteins, these cells become invisible to the immune system and to our current antiretroviral treatment strategies. So the major push now for HIV cure research, in parentheses, is that there are intense efforts now trying to reawaken HIV from its quiescent state or latent state to allow these genomes to be expressed. And the work described yesterday, the CRISP and Cas9 cascade, there's really intense efforts now trying to clip these genomes and modify these genomes in infected persons using the enzyme systems described yesterday. So this is really forms the major framework for the barrier for curing HIV. This is one reservoir that's been well characterized. There are other reservoirs that are discussed, such as reservoirs within the central nervous system, but this is a very hard site to be able to study in HIV-infected individuals. What I do want to point out is that while the virus is quiescent in these cells, at any time point this virus can become reactivated and reestablish infection, either through encounter with its cognate antigen, the antigen to which it's derived, or under permissive cytokine conditions. And so these are the studies in HIV-infected adults, really emphasizing that we cannot cure HIV with our current combination antiretroviral treatment. Again, Bob Selkana's lab looking in HIV-infected adults over a time frame of 8 years of antiretroviral treatment and looking at the frequencies of these infected resting memory CD4 T cells carrying replication-competent virus. And from these individual time points representing a single measurement of the frequency of infected cells in a given individual, over time he estimated the half-life to be 44 months. So quite different than the one-day half-life of the activated cell or 2 to 4 months of the slower turnover population, leading to the conclusion that HIV is really not curable. And so this is where we are really today, except for the one person who's been cured of HIV, is that it is incurable but manageable with lifelong treatment, which is life-saving for these patients. So this is the basic framework and model that I've been working on for the past, since 1997. And the basic idea here is that in perinatal HIV infection, the infection is established in the context of a fairly naive immune system. Most of the CD4 positive T cells are naive, they're not memory. And so if we hypothesize that if you can block infection events very early on, you can then block spread into these viral reservoirs and potentially achieve a curative outcome. And so we obviously started with looking at kids who had delayed treatment because we had many kids in the US who did not have access to treatment because they were not available at that time. Combination antiretroviral treatment didn't become standard until the late 1997s. As I mentioned earlier, the epidemic started since 1982. So we had a lot of cohorts of older children who were infected that we could actually look at this phenomenon on what's the effect of delayed treatment on the reservoir size. And then as we move as we move forward, we can actually look at very early treatment and early treatment on these reservoirs. And so, as I mentioned earlier, the unique aspect of the immune system in pediatric HIV infection is what could potentially enable us to achieve virologic remission and cure. And what you see here on this side is really the proportion of T cells or CD4 T cells that are memory T cells in a newborn. And as you can see, it actually takes up to 20 years to reach your complement of memory T cell generation. And so this is our first study in pediatric populations, really to first establish does this reservoir exist in children? Can we quantify these reservoirs using the standard methods of virus co-culture? And what is the frequency of these infected cells in children? Is the dynamics very similar? And most of the studies, as you'll see, are really based on small numbers. There was prior to the new charge of trying to find a cure for pediatric HIV infection, there really hasn't been much emphasis on reservoirs in children and trying to understand reservoirs formation. It's been my focus of research, but it really, for the field at large, it really wasn't a major concern. The major focus really has been on preventing infection and treating infection. But our studies on viral persistence and the dynamics of these compartments over the past 15 years has really informed our HIV cure agenda for pediatrics, and has really set the framework for our studies going forward. And I think it was this commitment to this sort of work and emphasis on reservoirs in children that led us to the identification of the case of the Mississippi child. So what you see on this slide is really kids treated during chronic infection, meaning started around 8 years of age, which is very late. The reservoir dynamics is very similar to what you see in adults, as I showed you on that slide. There's a stable persistence of these infected memory CD4 T cells over the time course of treatment at about 1 per million resting CD4 cells. So we then went on to look at what's the effect of treating kids early. So as I said to you, most HIV-infected infants can be fully identified as infected really by between 2 and 6 weeks of age. And that's generally when early treatment is started in children. It takes about that long to diagnose a child, get the parents ready for treatment, and start antiretroviral treatment. So in the context of this study, this is a study that was conducted in the US and Brazil. We looked to see to what extent starting therapy used early, meaning by 2 months to 3 months of age, affect the reservoir size in these children. And what you see, these are infants that were enrolled in this trial, and we followed them over 2 years. We looked at 6 months, at age 6 months, about 48 weeks of study and 2 years of treatment to see the reservoir, the quantity, and the decay parameters of this reservoir. And this is what's striking. Even infants treated as early as 6 weeks of age, but at 6 months of age, we can readily detect a replication-competent reservoir in these children. The reservoir decays somewhat through 2 years of age, but essentially by treating 6 weeks of age, we didn't really affect the overall frequencies of infected cells in these children, where the frequency is about 0.3 per million. The circles in red show the children who were treated before 6 weeks of age. So there was a suggestion that if you treated before 6 weeks of age, you can actually restrict the size of the reservoir. Now, prior to the HIV cure research agenda that started a few years ago, we didn't really know the clinical relevance of getting to a reservoir size of 0.1 or 0.01 versus 1 per million or 10 per million. But it's becoming apparent from few case studies that if you can really, and Bob Tilkana's group has modeled this, that actually size really matters. And if we can get the reservoir, what he's projecting is that you would actually need to achieve a 6 log reduction in the size of this reservoir to be able to get to a point of virologic remission where patients can go off treatment for a lifetime. So that's a very large target to try to reach with current antiretroviral treatment. But I think what it's telling us is that certainly by starting treatment early, while you don't prevent establishment of the reservoir, we can at least very early on restrict the size of the reservoir. And so perhaps with other adjunctive strategies that try to either reactivate virus or reawaken virus or clip out viral genomes, we may be able to achieve this in the next 10 years or so. And so we've done follow-up studies to see, well, are the patterns of persistence different in kids who are treated early or not? Again, these are small studies of children. This is a group of 12 children that we did a follow-up study looking to see, okay, if you've been treated at around 2 months of age, what if we followed you for your suppressor 5 to 6 years? Does the virus, amount of virus in your body change over time? And this is what was striking. When you do standard antibody tests, most of these children, 67%, will test antibody negative. And what that means is that you've restricted the virus from replicating early on, so you actually don't even develop an immune response to the virus. But even though these children were testing HIV antibody negative, when we do our ultrasensitive viral culture assays, we can still recover virus from 83% of these children. And using ultrasensitive viral load genotyping assays, most had ongoing low-level viremia, which means that the virus could still be activated, or was still being activated. And so this was, or look at a long-term outcome of early treatment, meaning at 2 to 3 months of age. We then went on to look again, these are small studies, 4 children who were now suppressed. They were treated at 2 months of age, but now suppressed through adolescence for 17 years. And what we can see, what we're beginning to see is that the dynamic of persistence is very different in these children. They have very low amount of infected cells. So on average, an HIV-infected child or older adult has about 100 to 200 proviral genomes per million PBMCs. In these children, it's less than 10. Some it's not detectable. Replication-competent virus is very difficult to detect in these children using large amounts of blood. And most are HIV seronegative, again showing that with early treatment, we're really restricting the amount of infected cells in these children, and the pattern is persistent. And so what we, through 2014, we concluded, not surprising, that even with early treatment, meaning 2 to 3 months, HIV is not curable, but that we do see there are unique outcomes of this early treatment that we need to capitalize on. And that is we can limit reservoir size and also limit the amount of virus-producing cells. And so we believe that this provides a very strong rationale for consideration from HIV immunotherapy, such as therapeutic vaccines or monoclonal antibodies to provide immune cover when the virus reawakens in these children if they go off antiretroviral treatment. And so I'll come to the case now of the Mississippi child, and it's unfortunate that Hannah is not here today to discuss her management of this child and close follow-up and attention to detail and really investment in research and moving this agenda forward. And this case really fits with our model. I showed you that starting treatment late doesn't change the reservoir properties and characteristics in children, late meaning 8 years of age, but when we start at 2 months of age, the reservoir is established but present at a low frequency. And now this is getting to the left-hand side of the funnel, where if you start therapy very early. Now, in this case, as most of you have heard, this case got a lot of media attention, and the media attention was good and it was bad. I mean, the good aspects is that I think it's put pediatric HIV, a cure research agenda in the forefront. I think it's easy for us to, and I'll get to our clinical trials that's planned. It's easy for us to engage parents and families in a conversation about cure research, which is complex ethically, but around the world. And so this case has really helped the pediatric cure agenda. Now, irrespective of a cure agenda, what this case has done is really put a spotlight on identifying infections early in infants, so focus on testing and treating early, which the numbers are very dismal in terms of the proportion of kids globally who are on antiretroviral drugs. So even if we don't end up curing HIV infection, I think this case has really moved the field already with a focus on pediatric prevention, care, and treatment. And so in this case that we encountered, so within 3 months of identification of this case, we were able to evaluate this case sufficiently because we had the tools in place. We've been studying HIV persistence in children for over 15 years. So we were able to really characterize this case within 3 months to report in a closed meeting to the NIH that this was a very different outcome that we've ever seen before. And it was really only in teasing back and trying to figure out why was this kid different than any other child that what we identified was really the timing of initiation of early antiretroviral treatment. And that treatment started between 30 and 31 hours of life in this child. Most kids don't start treatment until several weeks of age. And that, we believe, was a distinguishing feature of this case. So this was a child who had clear evidence of HIV infection, shown by the closed symbols with detectable plasma virus through 19 days of age, also had DNA detectable DNA detection in circulating cells, was placed on combination antiretroviral treatment, had the typical decaying plasma viremia that we see, and then sustained suppression of virus replication showed in the closed symbols to less than 20 copies per ml. Now what you see here is off antiretroviral treatment. While most kids rebound within 2 weeks, most infected individuals will have rapid rebound within 2 to 4 weeks. This child did not have off antiretroviral treatment any rebound in plasma virus off treatment. During this period of antiretroviral treatment, we did all the sophisticated testing I mentioned to you earlier. We tried the cultural replication competent virus. Over 64 million cells were cultured over the duration of this follow-up. And again, no replication competent virus was detected. We could detect no free virus circulating in plasma using our most sensitive assays of less than 0.4 copies per ml, and no HIV-specific immune responses. So to us, this case was very distinct than any of the HIV-infected cases that we had encountered in the past. As I said earlier, this is a typical trajectory for when an HIV-infected person goes off antiretroviral treatment, irrespective of how long you've been on antiretroviral treatment. The virus rebounds within 2 to 4 weeks. And so from the Mississippi case in 2013, prior to rebound, our hypothesis was that starting therapy very early led to prevention of establishment of a long-lived HIV reservoir in this child, and that's why we had achieved this state of functional cure. And we used the word functional cure, not cure, because we knew we needed some sort of follow-up time to figure out had this child been cured or not. And the terminology in the field at the time that we reported this case was cure, sterilizing cure or functional cure. And the difference between those two states really depends on your capacity to detect persistent infected cells. So with sterilizing cure, you're off antiretroviral treatment, there's no rebound, and there's no detectable infected cells. With functional cure, you still have detectable infected cells, but your immune response plays a role in control of infection. Now in this child, there was no detectable immune response that we could find, but we didn't want to say cure because of, in terms of being very conservative about the finding. And so these are the data, disappointing for the child, disappointing for Hannah, and disappointing for us, but I think this case really informed the field. And that is that I don't think anyone would have expected virus to emerge at 27 months after complete quiescence in an infected individual. And it was really Hannah's attention to follow up with this child, closely following this child, that we were able to capture within 4 weeks the rebound viremia in this child and genetically characterize the virus. So the child was replaced on antiretroviral treatment and has responded to therapy and is now has control of viremia. And so this is just to point out that during the period of virologic remission, there's really no evidence of any HIV-specific immune responses using antibody testing or CD8 T-cell responses that were done in Catherine Azuriaga's laboratory. Again, suggesting that there's no active ongoing virus-producing cells during the period of virologic remission. But with rebound viremia, what you can see is a prompt response in terms of humoral HIV-specific immunity. So this child is quite capable of developing HIV-specific immune responses with a fully developed Western blot reactivity to all of the HIV proteins. So again, confirming, or at least in support, that HIV was in a quiescent state during the period of virologic remission. Now, obviously, there's been intense interest around the world in identifying additional cases like this, and this is just to caution the field. There are 3 additional cases that were identified who were treated very early, birth to 7 days. The Canadian child, the Dublin child, and the Milan child. And these children are antibody negative, have no detectable DNA on antiretroviral treatment. But what you see here is when they went off treatment, all of them rebounded within that 7 to 14-day window. So there's something distinct about the Mississippi child that we still don't fully understand, and we're really continuing to examine. Nevertheless, what this shown us is that there's perhaps hope that very early treatment can enable a state of virologic remission where a child can have time-limited heart and go off antiretroviral treatment. Now, this is 27 months off antiretroviral treatment, which is quite a long time. Now, obviously, the whole field of HIV cure research has been re-energized by the single case of cure in Timothy Brown, the Berlin patient who received a stem cell transplant with specialized cells that has led to cure. And he now, I'm a little cautious about using the word cure, so he's been in virologic remission now for 7 years with this treatment approach, and has to date, as far as I know, no evidence of reemergence of viremia. And this case has really has been the catalyst for all of the NIH's efforts towards HIV cure for patients. what the Mississippi case has done for the pediatric agenda, and I think has, and again on this theme as how studies in children have informed the field, I think is to really be cautious and think about, we could really never declare someone cured of HIV. We really need long-term follow-up studies, sort of analogous to cancer chemotherapy. And so this is kind of our conceptual framework now for, and cure again is in parentheses, for achieving virologic remission and hopefully on a pathway to cure, where we can move our goal of HIV therapeutics from lifelong CART to some period of virologic remission, and hopefully in some we will achieve cure. Now this is to show, obviously we had to confirm that the HIV that emerged in the Mississippi child was indeed not reinfection from some other source. There was no evidence of sexual abuse in that child or pre-mastication, needle stick injuries, anything to suggest that this was a new infection event. And what you see here on this slide is we phylogenetically map the maternal and infant sequences. Maternal sequences are in red, orange, and infant sequences are in blue. And these sequences, as you see, they're phylogenetically related and completely distinct from the other infant sequences that we've studied in the laboratory. So this phylogenetic relatedness really confirms that HIV in this child reemerged from a latent quiescent reservoir, which we believe fits quite nicely with the model in resting memory CD4 positive T cells. So what's the lesson from this is that we believe this single case, now there's still a single case in adults, so we believe for pediatrics, this is our equivalent of the Berlin patient. The Mississippi child provides us with proof of concept that very early therapy may enable remission, but I strongly believe that we need immune enhancing strategies such to protect reestablishment of viremia when virus emerges. I will say again on the theme of very early treatment, it's a very complicated slide, but just to say that there are now efforts in the adult world to treat individuals infected, identify very early infection, to look to see very early treatment in adults can achieve virologic remission, as in the Mississippi child. And this is one case from San Francisco, Haroy Hatano, showing an adult treated within 10 days of infection. And these are the types of studies that we need to do to define whether a patient has been cleared of HIV infection or not. And as you can see, these studies become very difficult in pediatrics because they include bone marrow biopsies, spinal taps, lymph node biopsies, ileum and rectum biopsies, leukapheresis. That's simply not feasible for pediatric population. So one of our major missions is actually trying to identify innovative and sensitive ways to probe HIV persistence in children. We know we'll need to do these tests at some point, but before getting to that point. And so I'll just end by saying, what are the next steps? So we now have a clinical trial. I'm the scientific chair for the Impact or International Maternal Pediatric AIDS Clinical Trials Network, HIV Cure Scientific Committee. And so we have a clinical trial that's now open to study this very concept of very early treatment in children. But I do want to end with what we still have a problem in pediatrics. There are 3.2 million children living with HIV, and while there have been significant efforts in prevention with 1 million infections averted, just in 2013 we had nearly 250,000 new infections in children. So while we can prevent, we also need to have strategies to treat towards virologic remission. And with respect to treatment in children, as you can see worldwide, only 23% of children are receiving therapy. So a lot more work to do with respect to antiretroviral treatment. And so I'll stop here with my acknowledgments. Hannah Gay and Catherine Zuriaga, who have been the sentinel in this work on the Mississippi child, and the people in my laboratory who work endless hours on handling each sample in a very precious way, and the funding organizations. Thank you very much.
Thank you, Deborah. That was really elegant. I had read about the Mississippi child, and then last Thursday and Friday, doing a review at the University of Maryland Medical School, talked with Bob Gallo. He was equally disappointed by the vaccine. Which do you think is going to end up being the way out? And the other point or question is that Gallo said that the incidence in Baltimore and Washington hasn't changed. It's still about 20%. Does this mean that we're going to have continuing infiltration of HIV virus into the population?
So that's a great question. So with respect to vaccines, I know the field of HIV vaccines has been quite disappointing, but the Thai trial, the RV144 trial, shows some hint of protective efficacy. The field of broadly neutralizing antibodies is exploding, and so we have some clinical trials planned in a proof of concept way to see whether broadly neutralizing antibodies coupled with antiretroviral treatment can affect virologic control of antiretroviral treatment. I think there's now been a renewed look at vaccines for a therapeutic approach. I think for a cure agenda, we certainly need immune enhancing strategies. You know, HIV is not different than any persistent viral infections, you know, VZV, herpes, where EBV, where you need an adequate immune system to control recrudescence of virus. So I think that with the efforts we have now, and especially focused on a cure agenda, I mean, prevention still is our mainstay. It should be our mainstay of all of these efforts, but as you mentioned, the epidemic still continues. With respect to the epidemic in Baltimore, it's really a very big problem, and now there are really implementation science that's going on in terms of PrEP, pre-exposure prophylaxis, post-exposure prophylaxis, promoting condom use, safe sex behaviors, and really trying to get at an implementation level. Because it really takes a long time for science to translate into an implementable plan. I think the mother-to-child transmission model, the perinatal transmission model is really a good model because we went from 25 to 40% risk of transmission to less than 1% in 2 decades of this. Hopefully we can move it a lot faster. So I think I'm hopeful that the efforts that are now being focused on prevention and implementation will really affect the epidemic in Baltimore, most of which is in young adults and young gay men. It's a hard to capture population, but we can't ignore the problem.
Thank you. Really interesting talk. I think I was struck recently, this HIV is not really my area, but I have become a little familiar with some of the work in South Africa.
Mm-hmm.
And so I was curious, first of all, do you take into account the breastfeeding of the women? And what I was really struck by in South Africa is that they will, of course you have the balance between the malnutrition and, and the potential benefits of breastfeeding, but then also, even if the child is deemed early on as HIV uninfected, the mother is still infected and, they allow for the breastfeeding to occur. Is that smart? What do we know about that? And, are there antibodies that are protective not only against other diseases, but perhaps are there, neutralizing antibodies that are present in colostrum that could be beneficial?
Well, thanks for bringing that up. I mean, breast milk transmission is fascinating because, kids are fed gallons of milk and then something happens and then the kid gets infected. But the best thing about the trials that have been done, they really set the framework for prevention, and it's all about prevention. And so prevention of breast milk transmission, there are 2 ways we can do it. And so there's a big focus now on what's called option B+, which is giving all pregnant women antiretroviral drugs. So we know the key to transmission is really viral load. So if you can control viremia, you can control transmission. And similarly, you can control breast milk transmission. So our studies show that antiretroviral drugs prevent transmission. So it's now standard for women who are breastfeeding to, what's prescribed is really to take antiretroviral drugs throughout the breastfeeding period. Now, having said that, the big obstacle to all of this, a lot of women get infected during pregnancy. So a negative test at the beginning of pregnancy doesn't mean you're negative at the end of pregnancy. Women get infected, and in fact, with primary infection transmission rates are quite high, up to 30 to 40%. And so you can get infected even during breastfeeding and not know they're infected. So that poses a challenge. But we definitely have mechanisms to prevent transmission throughout the breastfeeding period, making it a safe and affordable practice. In the US, obviously, we don't advise women to breastfeed because formula feeding is affordable and safe. But in those settings, what's being offered and the
social justice question.
Well, the transmission rate is less than 1%. So when you're living in a situation where your mortality rate from not breastfeeding way exceeds the risk of transmission,
It becomes an economic issue.
In the United States, the AAP and the Academy of Breastfeeding Medicine both recommend continued breastfeeding and obviously prophylaxis during and before. So for AAP, Academy of Pediatrics and the Academy of Breastfeeding Medicine both have the same recommendation in this country and worldwide.
But
Right, but the implementation worldwide is not affordable,
no, but I think one thing to remember, healthy mom means a healthy baby. And so what this does, it actually provides drugs for women to get treatment. And, so you're actually taking care of the woman too at the same time that you're preventing infection to the infant.
Right, globally, just not as well implemented, that's all,
Yeah, no, I think they're huge challenges. It's nice to sit here and say we have prevention strategies, but implementation is where it really is. And that's why I ended with the slide, 240,000 infections despite the progress. But we have made progress and we'll continue to make progress.
And this is a tangential question, but because of the story of Henrietta Lacks and Johns Hopkins, I'm sure there's a great sensitivity to ethical issues in terms of what you're doing. I was wondering whether you can say how that affects you.
Yeah, so the question has to do with ethical issues surrounding this work, and they're huge ethical issues, and the parallel with Henrietta Lacks and my link to Johns Hopkins. I will say, when I reported the Mississippi child, I did it really naively, not really realize. I did it for the interest of science, and I felt that this was a very distinct case. It has potential to inform the field, inform our direction, inform investment in pediatric care and treatment. And I thought, to the best of my knowledge, I was as cautious as I could be in describing the case. I certainly didn't expect 27 months later for rebounding virus. I mean, we didn't expect that. But having to do with the ethics of cure research, and what happens is when you're in a time when your transmission rate is 1%, and you're saying we should treat kids early, it means exposing 99% of potentially uninfected children to a combination drug regimen that we don't fully know the toxicity profile from a newborn. In fact, we don't even know how to dose these drugs in this setting. And so the ethical framework is very challenging, and it's why I highlighted the PSCTG 076 trial, is that the ethical framework for that was just as great, because we were taking an underrepresented minority, women and pregnant women, and giving them a drug, AZT, that was just FDA approved for treatment. But it was done, and it was done, in the spirit of the discussion this morning with the PXE gene. Mothers want to protect their children, and they'll do anything to protect their children. So we do have, the NIH does have an ethical board, and all of these trials are vetted through that board. In fact, we wrote a manuscript that was published in Lancet on the need for ethical foresight, just in general in cure research. I think the biggest ethical struggle that I have is the frenzy around the word cure. And I think, we just need as a field to get away, we have cure-related trials, cure funding. We need to figure out how to make cure not equals cure, but some other, stand for something else, and shift to virologic remission. So I think we've learned a lot in terms of metrics and follow-up for our clinical trials. I mean, I think rebound of 27 months means we need to follow these kids for 10 years to say, have they really been cured or not? But it's so the ethical framework exists. I think the issue with tissue sampling, that's where we really have to figure out which direction to go.
Some of the long-term effects of the drugs have,
Yeah.
possible studies?
So that's a great question. I think it really justifies a cure agenda. Kids become elderly individuals by age 20. They have osteoporosis, poor stature, diabetes, heart disease. There are many long-term toxicities of antiretroviral drugs. So if we move the clock down for treatment to a neonate, and they're living 30 to 40 years, it's a lifetime of treatment. And so we need to come up with creative ways, immunotherapies, periods off where they cannot transmit to, as they age up into adolescence. So it really justifies a cure or a virologic remission agenda.
And in adults, can they tell the effect of long-term drugs on pregnancy?
So in adults, it's well established that they have, kidney disease, bone disease, heart disease, from long-term toxicity. Yeah. Diabetes. Thank you.
Deborah, that was brilliant. I can't resist asking this question. You are a terrific role model. You've really done some beautiful work. How can we, how can you advise us, from your perspective, how can we get more underrepresented minorities into science, medicine, engineering, physics, oceanography?
I think it's all about having role models at a young age and educating them from a single parent household. So I don't think fathers are essential to success in the field. You just need a parent. You need a parent who's devoted. My mother didn't finish high school but felt education was the way for her girls to actually have a better life. And so how do we, so at Hopkins we have a Center for AIDS Research that's really focused on engaging high school students and college students into biomedical research at a very young age. And the talent is there. I think we just need to be very active about mentoring and continuing to mentor. It's not just what's been very rewarding for me is the undergraduates and college students, and particularly that I've mentored, who've continued into biomedical sciences. And 10 or 15 years later, I still get follow-up, I'm doing this. And I think that sort of connection really helps. But we have to be very active, and this thing about women in science, Hopkins, there's this whole discussion about how to improve women from falling off the tracks. I think we just have to start acting and stop talking about it. And the idea of a quota or having some funds earmarked so you at least have a certain amount of individuals that are along this track is probably the only way I see right now to really change dramatically the numbers. But I think by engaging in our community at Hopkins certainly is the way that we can make a difference in encouraging underrepresented minorities.
Thank you very much.